All right, welcome everyone to today's webinar. We got blower door testing and its impact on HVAC design and sizing. So as always, today's webinar is being recorded. It will be uploaded to our YouTube channel, which you can find by either searching Spear on YouTube, or you can go directly to our website at eepartnership.org. Under our news section, you'll find our resources page. We've done a lot of improvements to the website. There's a lot of more information on there. Fletcher is doing a great job with that. Once you're on our resources page, you'll find a link to our channel. We have over 150 plus videos that are on there, a variety of topics, a lot of it about energy, and then also Sean's CELC program that she's got. Today's webinar, as always, is also eligible for the ICC CEUs. You must be present for at least 3/4 of the presentation. Within about 72 hours, about 4 days roughly, you'll receive a course evaluation from Kathy Lawrence. Please complete the survey and send it back to her to receive your course completion certificate. With that, you'll find the title and course ID, and then, of course, you can keep that certificate to post on your account with ICC. Lastly, as always, we will have the chat feature open. I see a lot of people in the chat saying good morning. Good morning. Thank you for joining. Please report any technical difficulties that you might be having. I think we've got this down pat now. Q&A feature is also open. Post any questions that you have there. And again, thanks for joining. Let's get this started. So if you're new to Spear, always have to go through some housekeeping. If you're new to Spear and it's your first time, welcome. Thanks for joining us. We actually provide trainings, webinars, in-person, field training, as well as IECC test prep training, which I have some later this week. For any of you looking to get certified, so what I do is just kind of help you walk through the study guide with the IECC and get you prepared for the test. So I can also help with any questions regarding the energy code, ASHRAE 90.1. We've got a new version out now that's the 2024, which everybody has a lot of questions on, and then the 27 is currently being written as we speak, having committees. For that, I can help with any questions from plan reviewers to building officials to third-party energy inspectors. I'm always welcome photos from the field. That helps a lot with what I do as well. So we also assist cities with the adoption of the 2021 and or the 2024. We can also help them navigate the additional amendments to help lessen the impact of the adoption for your building community. My contact information will be at the end of this presentation. Please feel free to reach out to me if you have any questions. Always love to help in any way that I can with the energy code. And now, of course, with P&L and ResCheck being on a pause, I also can help answer questions about ResCheck and ComCheck if you have any specific questions on that. So we've talked about this previously on many webinars, but I just kind of wanted to wrap this into and connect the dots to how does blower door affect HVAC. Well, we'll start off first by why does air tightness of that building actually matter? So blower door results, the tightness of the home significantly influences HVAC design and sizing. We'll see more about why later on. Designing the HVAC system without blower door data also often leads to oversizing and worse, just by putting worst case leakage, and then it's better than that. Now the system's oversized. This, of course, results in higher upfront equipment costs, poor comfort and efficiency, poor humidity controls in the warm and humid climates, which most of Texas is in. So as we go through this, you'll see how all this ties together. But to continue with that, a tighter home increases energy efficiency by reducing loads required to heat and cool the home. It increases the indoor air quality by better control of infiltration of the air that contains contaminants and pollutants. It also increases comfort for the occupants. It prevents drafts, temperature, and pressure imbalances throughout the home. It basically saves the homeowner from having to turn down that thermostat or turn up the thermostat because of the pressure imbalances or temperature differences in the home. Lastly, it also helps enhance the performance of the HVAC system by ensuring that they are correctly sized and will control temperature and humidity by allowing longer run times. That usually will draw down humidity and get it a drier air, and it feels more comfortable and colder to most people, and they can actually result that into having a higher set point on your thermostat. So we always hear this. I hear this phrase a lot. Houses need to breathe. That's kind of what they always used to say. Houses need to breathe. They do. but we want to control how much, how often. So mechanical ventilation can be thought of kind of as a controlled infiltration. So uncontrolled infiltration is basically when the house breathes on its own. So what do most people mean when they say houses need to breathe? They're most concerned and worried about is, well, if it can't breathe, there'll be moisture buildup. It'll be mold, it'll be mildew inside the house, the indoor air quality will suffer, we'll have stale and stuffy air, stagnant air that's inside the home. They often assume leaky construction also helps air out the house um, naturally, but that's, it's best. There is some programs that are out there that we do require some airing out of the building to kind of reduce some VOCs that are inside the home, but we should not have uncontrolled air moving in and out. That basically spawns from a belief rooted back in the construction methods back in the pre-70s where homes were naturally drafted. If anybody's on here that's been framing for long enough, there was balloon framing that we just basically allowed air to move up and down inside the building shell. And that basically kept the house dry, and it also helped control temperature inside slightly. So if we have the known target based on square feet and number of occupants, talking about mechanical ventilation, then we can measure it and ensure that the correct runtime is set. We'll talk more about ventilation in a minute, but that's, as I said just a second ago, we want to control how often and when. We want a known CF film that's coming in so that we can set that runtime to meet what's required for each occupant and each square feet inside the building. That's our main goal, our main objective. Having uncontrolled infiltration is not a good thing. But here's what we know. So from a building science standpoint, houses don't need to breathe. People do. We should know that by now. Houses don't need random air leaks. They need controlled ventilation. We just talked about why that is. And then leaky homes allow for unfiltered, uncontrolled air, moisture, pollutants, insects, allergens to enter. It's not ideal for a new construction home. Moisture problems are also often due to poor vapor control and not just tight envelopes or having non-tight envelopes. So vapor is also one of those things. In Texas, mostly, we don't have plastic behind the sheetrock. We don't have vapor barriers in the walls. We want vapor to be permeating through the building or into the building, whichever is the driest is where it's going to go. So we want buildings to dry to the outside or dry to the inside, depending on the outdoor condition. But we also don't want to have holes there either. So vapor is allowed, but air is not. And that's kind of what we try to control. So why are tight homes better? At some of the stuff I just read, it kind of goes without saying, but airtight homes are more energy efficient. That's one thing that we lean towards very heavily. Of course, less energy is wasted on heating and cooling what is leaking through the holes in the envelope. And of course, moisture stays out if vapor and air barriers are done correctly, and then mechanical ventilation brings in fresh air when and where we want it. So it can be tied into the HVAC system directly, or it can be dropped into a common area like a living room or a foyer, just to mix in with the home's air that's already currently there. In the most cases, and I know what some people will say, depending on what location you're in, most of the time with a new construction, outdoor air is, as we would call it, fresher air, fresh air, to be able to mix and dilute the inside contaminants, which are known as VOCs or allergens or pollutants that are in the building material that the home was just constructed in. Billy, I do see that you say had trouble signing in. I appreciate you being here. If you need any help, please let me know. So what is a blower door? And I'll just quickly kind of go through some of this. I'm not going to break it down to how we set it up and what's all the pieces, but what is a blower door test? Why are we doing this? Yes, we're measuring the air leakage in the building, but why? I mean, it's a good rule of thumb to measure the air leakage to determine how leaky the house is. But what does that tell us? It tells us that we're not going to have to overturn the air inside the building is not going to overturn drastically, so we're not going to have to keep conditioning it. So it rolls it back into sizing. But testing equipment that's used to validate that basically is the blower door. A blower door kind of roughly simulates 15-mile-an-hour wind hitting the house in all directions at the same time. That kind of used to be how we would say that, but it's not. I mean, it's not true to life. So it does not locate the leakage. It only measures the amount of leakage. It measures the air moving through the fan in CFM, and that's cubic feet per minute at a pressure differential of 50 pascals. That's a pressure difference from inside to outside. So the pressure could be anything. The difference has to be 50. That's the limit that's set, that's required by the standard and is written into the IECC. So during this time, the house is now experiencing a pressure differential from inside to outside at 50 pascals. Once the CFM is measured, it must be converted to be useful for us. So just looking at it and saying, well, my CFM was 2,438, that doesn't really tell me anything. You can have the manometer set up and tell you in square inches what size that hole is, roughly estimating how much leaking is going through the building. But again, it doesn't point where. So in the 2021, there's two ways to do it now. In the 2018 and prior, there's only one way, and that's ACH. 2021, 2024, going forward, there is two ways to do that. So ACH is the first and foremost. It's air changes per hour. It's calculated by taking the CFM, multiplying it times 60 to convert to an hourly rate. And then you divide the condition volume. And then for foam encapsulated houses, that includes the entire volume of the attic. Once you divide the volume into that hourly rate, then you get an air changes per hour. I won't go through what all those are because the targets vary from climate zone and code cycles. They were roughly the same for a long time. Now it's being adjusted in the 24, and it'll continue to kind of tighten that building envelope as we go into new code cycles. The second method, though, is actually getting CFM per square foot of condition enclosure surface area. So that includes the walls, the floors, the ceilings. The total surface area is now divided into the CFM to get a 0 point something value. Right now we're looking at like 0.30. That is how much CFM is happening per every square foot of condition enclosure surface. So the CFM, that also, again, varies. It's going to vary on what pathway that you're using. And so in the code book, that's what that'll say. I'm not going to go through all of that. There are some exceptions, though, that are written into the 2021 and will be in the newer code cycles that goes forward. That basically is for like apartments in R2 buildings and any house or dwelling that's 1,500 square feet or smaller. What we started seeing is this rental property being built, and it's just shrinking the square footage. And some of them are less than 1,000 square feet. They're 800 square feet. They don't have a garage. They're not an encapsulated home. They don't have a lot of volume. So to get to a very tight, even a 5 ACH or a 4 or a 3 is nearly impossible if you just don't have the volume of air to do the calculation to get there. So they came up with that CFM per square foot of condition enclosure surface. This allows for tighter buildings to have a higher ACH but still be compliant to the code. For example, an 800 square foot apartment can roughly test out at, if you did the calculation, at a 6 or 7 ACH or possibly higher, as long as it's below that 0.30 or 0.27 CFM per condition floor area respectively, and that's due to changes in the code. So that helps with smaller buildings. And if you're in a city that are still on the 18 and you've got this rental property being built, or just smaller homes in low-income housing, let's say it's 1,100 square feet, it's 1,200 square feet, they're decent, but they're small homes. Adopting something like that to help them not have to continually fight to get below a 5 ACH or a 3 ACH or a 4 ACH, this can help speed the process up and not hold up closing and CO of the building. So it's one thing that you can do. I can help with that if you want to call. We can go through and try to put something together that you can put on your website or your builder's packet and just let them know that there is a different way to get there. So that'd be something you can look at to say, is it the same and equal to? I mean, as the smaller buildings go, you just don't have the volume to be able to get to that tighter ACH. Then, of course, since wind rarely, unless you're directly overhead with a tornado, does it hit the building on all sides at the same time. But in addition to wind, the blower door can simulate pressure differences that can happen in the real world on a house. The taller a building is, the more of what's called stack effect starts to take place, which is air moving due to buoyancy. The warmer air is more buoyant. It actually starts to rise over the colder air. And then, of course, what needs to be replaced below that positive pressure plane is actually going to be colder air. So as air rises, you can see in this illustration, it creates a positive pressure at the top of the building, negative pressure at the bottom, and of course there's a neutral plane there. So as that air starts to rise, and this happens naturally, if you've got a home that is, especially if it's a newer home, if it's got tall ceilings, next time you're on a ladder and you're changing a light bulb or something, once you get close to that ceiling, you'll feel it's much, much warmer at an 11-foot ceiling height or a 12-foot ceiling height because the heat is pocketed there. That stack effect at its finest, and that heat is rising and it's pulling it in through the windows wherever it can get through the envelope to get newer air to replace it. So, of course, having that wind and then outdoor pressure can also cause air movement in and out of the building. So, as always, you can see at the bottom, if you know anything about the wind currents and all that, you've got a windward side, you got a leeward side. If you have, and again, it won't happen on all sides at the same time, but if you have a 15 or 30 or we've had 70-mile-an-hour winds here in Dallas just recently, but if you have that wind hitting, it's going to be positively pressuring that side that's getting hit by the wind, and the opposite side, as the wind goes around it, it's going to create a negative pressure and it's going to start sucking air through the holes in the building. Sometimes you'll hear that from windows whistling or doors whistling. It depends on how that air and how strong that air is moving around the building to create a negative pressure. So those pressures actually help. It just moves the air in and out of the building through all the holes in the envelope. That's what our blower door is trying to simulate so that we can prove that things either are meeting the baseline threshold that we need for ACH or CFM per condition enclosure area, or it needs to be fixed. So the benefits of using real blower door data, though, is, and we'll see more of this a little bit later, is basically real data equals real load accuracy. Everything that they turn into you for permit request is and I'll just use it this way, is a hypothetical or it's an assumption. It's a preliminary or projected model to say this is what we feel that we're going to do. These are the test results we feel we're going to accomplish. And of course, sizing is now based on those assumptions. If the HVAC guy is not doing the correct assumptions, we'll see what that looks like a little bit later, but that changes everything about sizing in the building for when it comes to HVAC. So it can prevent over and undersizing, which oversizing is the worst option. It supports the energy code compliance because it requires it's been a requirement in code for several cycles. There are still areas of Texas and, of course, across the country that don't require blower door testing or they don't require duct testing. So there's no validation that's happening. So even though there's something that's projected or assumed, it's never verified as a reality. So we have no idea if that actually is the right size or not. And of course, smaller loads enable the possibility of using higher efficiency or possibly ductless systems. So sometimes you can eliminate ductwork. So if you can get a building tight enough and it's small enough, or even if it is a standard size home, you could possibly put some mini splits in there and put a couple of head units, and now we're not having duct leakage. So it eliminates that duct leakage and friction loss of poorly installed ducts, which we've talked about on previous webinars. You eliminate that altogether. So much more high efficiency equipment. And of course, we've always talked about this multiple times. Anytime we talk about HVAC, we always go through the manual J and S. That never gets old by saying that. They are required by code and they must be collected and verified for today's types of building construction. So manual J isn't any good unless you also collect manual S to compare the BTU output of the equipment to the BTU of the loads that have been calculated by the manual J. But here we see an example. Looking at the difference in leakage. Again, this is being assumed when building the model. We can put super tight, we can put tight, we can put moderate, we can put leaky. If an HVAC guy always picks leaky because That's the way he does it, and it sells bigger equipment, and the building is actually being constructed that's going to be tight. That is off in sizing. That's a complete disconnect from reality of what's happening. So we need to actually have the right data. We need to assume as close as we can and then test, verify, and then make sure that the sizing is correct. Keep in mind, though, the BTUs per hour that you see on here is from the infiltration load. It's not the building's total load. It's if we have real leaky houses, you're adding 6,000 BTUs of cooling on top of the loads that are already there from windows, walls, ceilings, and floors. So by what I've seen over the past 13 years in this industry, the majority of homes and residential apartments would and should be listed as moderate to tight. Again, if HVAC is doing their manual J at leaky, they're just overshooting it and they're trying to have bigger sets of equipment for something that is incorrect. So my house was built in the early 90s and it's still doing a blower door test qualifies it to be in that moderate range. Now, my builder used polyseal and sealed up the top plates with polyseal. It wasn't the best, but they did do that back in the 90s. Other builders didn't. So mine would be considered moderate. If I was looking at another 90s built home and they didn't use anything like that, it probably would be a leaky house. But super tight would be for high performance homes or, as we say, correctly installed foam encapsulation. I say correctly with air quotes because foam houses must always have their leakage verified by a blower door to ensure the super tight envelope was achieved. So a lot of places that I've seen that don't require blower doors, uh, their foam is being used. Over 60% of their building stock is being foamed, but it's not being verified with a blower door. Many, many times I've inspected a foam house that was installed correctly, the right R value, the right depth, but an electrician, a plumber, HVAC, low volt contractor, you name it, uses a foot saw and they punch a large hole through the thermal envelope. So now not only will that house have a much higher result, it could technically still pass due to the ACH that's low enough to pass the requirement for the climate zone. But that's now going to allow for humid air to become trapped inside the home's thermal boundary. And of course, that also now will cause a cascade of problems that cannot be solved without sealing the hole through the envelope. And without testing it and verifying it, you will never know until it's a homeowner complaint. So another comparison for leaky houses versus a tight. So this is assuming a 2,000 square foot home. As we can see here, 2,000 square feet, 8-foot ceiling height. The leaky house is 8 ACH and the tight is 3 ACH. The volume is roughly this is the same, 16,000. Now we have 6,000 BTUs of cooling due to infiltration on the leaky house and 2,000 on the tight. Same for heating. We have much higher BTUs per hour than it would be if it was a tight home. If you go all the way to the bottom, now you're seeing that the HVAC system size is 1 ton oversized. And of course, it does also change the ventilation rate that's required. The code does address the fact that if you have a leakier house, you can use some of those levels of leakiness in the mechanical ventilation to offset what's required for mechanical ventilation. But that's not a good rule of thumb to have it just leak profusely and then say that I don't have to do mechanical ventilation. But as you see at the bottom, a leaky house will only require 30, a tight house requires 60. The tighter the home, the more mechanical ventilation that we need, and the more it needs to be verified that it's happening so that the occupants do not have any undue stress over contamination or a buildup of VOCs or pollutants inside the house. So of course, being 1 ton oversized, that now is going to be what's called short cycling. So this is going to allow humidity to start to rise during those humid times of the year, especially during the shoulder seasons where those systems don't run long enough. And if it's short cycling, it really won't. You'll run 6-7 minutes tops, not even enough to get the coil wet, and then the system will shut off because temperature has been satisfied, but humidity is still there. On the flip side, though, if a leaky house was there, and we said this a second ago, if the manual J and the energy modeling calculations were using a tight house, but now there's a bunch of leakage, that's off. That's a missing target. Same thing on the flip side. If the modelers are assuming that it to be leaky and they build a tight house, now it's off as well. And then the capacity is wrong. So proper sizing of equipment to load can reduce equipment size, lower costs. It can also increase ventilation rates. We talked about that a second ago, but in some of the energy modeling software, like I said, infiltration rates can be assumed, and it can offset some of the need that's for the mechanical ventilation for the house. So another comparison here, this goes into more detail of the blower door, when the house was built, the older homes. Of course, you can also say the same with if you have a leaky house. It's built in 1995. The windows have been replaced and had air sealing done to it and more infiltration control. It's now actually changed the size requirement for HVAC. That's why in the coming cycles, you're going to see, even in existing system changeouts, it will require a manual J and S load calculations to be done to ensure that any improvements that were done still meets that sizing requirement, not a like for like equal to what's already there, because the system may be 30 years old. You're going to do a sizing calculation and make sure it's correct. All of this to say it's better for dehumidification and comfort control, lower first upfront costs. Builders are always looking to cut off or shorten or cut the construction costs. So, how much will a crew of doing polyseal or air sealing of the home, and they do a really good job of it, and you have a really good air barrier that you already have to install, is installed properly, now you have much lower upfront costs because the sizing of the equipment, if that is assumed correctly, is smaller than what it would be if it's going to be leaky. So I know most of them, the audience is probably asking, but that's comparing older homes to new homes. That's true. But there's a lot of weatherization that's now happening around Texas and Oklahoma that's actually starting to shrink that air leakage and infiltration inside of that. And just, I know they test in and test out. Requiring someone to have that data when you have an HVAC system changed out would be a good thing. So not verifying needs the older homes, the newer homes that are built, and not knowing how tight or loose they are. We just talked about it. Significantly challenges the sizing requirements for HVAC. So just basically all this to say, and I'm not trying to lose people. I knew I would do this. I go down the weeds a lot, but it's when a house, and we deal a lot with new construction. It's when a house is being requested for permit, and they're turning in documentation to the city for the permit. All of this stuff is being assumed. It's an estimation or a projection of what is to take place. And of course, now the third party and or whoever's doing the inspection needs to verify that what they've assumed and promised is being done. And then we'll talk about at the very end kind of a HVAC checklist to say we need to verify this. So, and all this is acceptable to go through, but if sizing's correct, then the home meeting those manual J, it's been done as well. So bottom line, design changes with tightness. So equipment size, if you have a leaky house, you have larger equipment. Tight house, you have smaller. It changes also the ducts. You can have smaller duct systems, or you can eliminate duct systems altogether. If you have a very tight house, you can use a mini split. Ventilation system, if it's a very leaky house, then it's an option for passive leakage that's happening with infiltration or uncontrolled infiltration. In a tight house, of course, it's required now, and it also is a controlled way of allowing infiltration inside the building. Runtime and efficiency, if you have a leaky house, it's most of the time it's short cycling. And then in tight home, you have much longer cycles that runs for more efficient and better humidity control. And also leaky, of course, if you've been in a leaky house, drafts a lot of times happen, and that's most people's first complaint. But I think I've mentioned it before. A lot of times when people feel air moving, it's not necessarily a draft. It could be the fact that you're sitting next to a cold window and your blanket of hot air around you is moving to that colder surface. And of course, having a tight house, you have much more even temperatures and better overall relative humidity control. It also does affect heating systems. Now, in Texas and Oklahoma, we're both predominantly a cooling climate. We don't require a lot of heating, but we do have heating in our houses. Most people now are not going to just not put heating in. But since that happens and we use split systems that uses the same air handler, this now can become more of a challenge because the heating can be grossly oversized because we need the fan speed and CFM for cooling. And then, of course, the newer systems will be able to have a dip switch or a tap that slows it down for heating so it doesn't have the same blast of air when it's hot. But the difference could be looking at colder climates and looking at that, and the same thing, 2,000 square foot home. This one's in Denver. If it's 7 ACH, you're looking at 4 tons of heating. If it's 3 ACH, you're looking at just around 3 tons of heating. And then, of course, if you have a 1.5 super tight high performance building, you're looking at closer to 2 tons. So that's, again, shrinking it down. But that's the difference of possibly either installing an 80,000 BTU furnace, which we see a lot in Texas, or 70,000, down to a 60 or a 45,000 BTU furnace. But also smaller duct systems as well, and smaller trunk runs. I know back again when my house was built in the 90s, and you talk to HVAC guys that used to do work back then, their biggest thing was, well, here's how we do it. We oversize the system by half a ton and we undersize ductwork. That's how they always did it, and it would meet in the middle to be efficient and effective to heat and cool the building. But all the ducts sound like jet engines, and eventually all the screws came loose from the vents because it was shaking itself loose because the velocity of air picked up from the smaller ducts that were not properly sized. That's what we're trying to eliminate as well. And of course, ventilation requirements. I won't go deep in the weeds with ventilation because we've had several webinars about it. But a tight home needs mechanical ventilation for good indoor air quality. We talked about what a contamination is. It's a long list of what is considered a contamination. New houses have off-gassing from new construction materials, and you want to either remove that or you want to dilute that so it doesn't have the parts per million high enough to harm who is or have respiratory issues or ailments in the building. Blower door results are used to determine and what's required for the ventilation rate under the ASHRAE 62.2 standards. The tighter the home, the more reliance we are on mechanical and planned mechanical ventilation rather than just uncontrolled incidental air leakage. For example, as we had a few slides ago, a leaky home is 30 CFM, met mostly by the house leakage, and a tight home is 60 CFM. That's cubic feet per minute every hour of the day, 365 days a year, running all the time consistently. That's 60 CFM that's required. And then, of course, if you run less than that, you need to multiply that to get a higher ventilation rate. And we just said a second ago, it does have an impact on ducts. So in the 27, I think it is, they're looking to add the manual D on top of manual J and S that are required already. So it's going to be in there that a duct design is also a requirement to turn in for plan review. So lower infiltration rates can reduce duct sizing, and that's the demands because the load by room loads are reduced, and then duct sizing becomes more efficient when loads are more accurate. If ducts are in unconditioned spaces like they usually are in Texas, envelope leakage becomes more critical. Any air loss also through the ducts is compounded by house leakage. So having house leaks can also pull and push air through ducts even if the system isn't running just due to pressure differences. And if you're having leaks, then you have conditioned air leaking out of that as well. So air leaks and ducts contribute to overall loss combined with envelope leakage, and then it greatly reduces the system's efficiency. Then, of course, it reinforces the importance for tight ducts. Having ducts tested and verify that they meet the requirement of the code it's mandatory, but it's also one of those things where it really just should happen on every single house. Design implications is smaller ducts equal lower material costs, of course, same as equipment, and then of course less static pressure, improved airflow and efficiency as well. So if we have older HVAC contractors on here, we just talked about a second ago, basically how they used to size it was oversize the system, undersize the ducts. Also, what happened with that is ducts, basically, if you had infield duct board transitions or Ys being built, that stuff would just blow itself apart eventually, and then you would leak a ton to 2.5 tons of air in the attic, and that's detrimental to the homeowner as well. So adding duct leakage on top of that is horrible. So there's a problem with all of that. It doesn't no it doesn't just not it just doesn't waste energy. It also decreases the comfort as well. We've talked about that before. So, not to mention poor performance of the system causing unrealized SEER efficiency and premature system failures. So, if you have a system that is not running to its peak performance, that's going to interrupt, even though you look like, oh, I've got an AHRI certificate that says I have a 15.2 system, but now you've got almost a ton of leakage in the attic, and you've got ducts that are compromised with how they're installed. That can now affect all the efficiency. So you're not realizing the potential of the system because of the way it was installed, and you've got a much leakier house due to the fact that the blower door uh, was not verified. So imagine if we built cars that way. I mean, it's if for HVAC to say half a ton oversized and undersize the duct. I mean, you can almost imagine being in a car that the shell isn't built enough to handle a wreck, but they're going to put a massive engine in it. It's kind of tough to see it that way. But today's HVAC systems are not cheap. They should all be installed per the manufacturer's installation instructions to achieve the highest possible performance and longest lasting of the equipment. There's something out there now. We went through it on a few webinars ago. Was the HVAC grading? What you're doing is just verifying that it is A, installed as the manufacturer's instructions, and B, the performance is at its peak efficiency so that it can actually run to its best performance to be able to condition the home and have better comfort for the occupants and do humidity control as well. And then, of course, speaking of humidity control, by having tighter houses and then the system being correctly sized, being that it has smaller loads, smaller duct systems, they run longer, it avoids short cycling. You can now eliminate some of that humidity that you see in older homes. A lot of times that picture you see at the bottom is just condensating on the inside of the windows. There's a lot of humidity trapped, and when it's hitting that cold surface, that happens a lot in cold climates up north, but we've seen it happen here in Texas a lot. What's the ideal humidity level inside of a house? They say basically the comfort level is 30 to 60, recommended is 45 to 55, and then high is anything 55 and above. And we've seen a lot of the foam encapsulated houses that have had a foot saw hole cut in the building. They're pushing that 80% or higher a lot of times, and the higher you get to the ceiling and closer to the ceiling you get, the higher that humidity goes, and there will eventually be a condensation point that will happen just inside the envelope, which is usually right below the ceiling, and that's where you're going to start to get some mold problems built up. I just saw one like that with this exact example problem in East Texas a few weeks ago. So it's new home, 2 years old. Having condensation inside the building and having mold is not a fun thing for a homeowner that was buying it for their retirement home. So real world issues, this is going to be kind of lengthy here, but all of this, when we go through all of this, it makes perfect sense on how we talk about it. But, why would someone not do it this way? And so glad you asked. I know we don't have the mics on here, but it's a long list. Let's start with who's responsible for ensuring all this is correct and correctly installed and correctly verified. This is something that isn't really talked about in the plan review or permit department or from a building official. Is this all depends on who's got it in their scope of work. So I've not seen consistencies between cities on how the energy code is being enforced and or inspected. So some cities collect only manual J and don't verify. Sometimes they collect both manual J and S, but they still don't verify. It's just turned in and collected. Others say they leave that up to the third-party verifier. But if the third-party energy verifier does not have this as part of their scope of work and they didn't do the energy model, they were only hired to do blower door and duct blaster, now it comes down to Is the city handling it? If it's not on their scope of work either, that means it probably is not being done. It's a good chance no one's verifying it. So sometimes I've seen where third party, a lot of times this happens with apartments that may be a residential style apartment, but if they're going for a HRVs inspection or above code program like LEED or NGBS, the National Green Belt Standard, that's what the rater's been hired to do, not verify it for code. They're only verifying it for above code programs, and the requirements for those sometimes are a little less stringent. It doesn't mean that they're trying to beat code. It like Elite and NGBS has a lot to do with site sustainability and water management and things like that. It's not only just looking at it from an energy standpoint. So there'll be things that the building department thinks is being done, or that every system is being tested, but LEED, NGBS, and HRVs can also still allow for a sampling protocol, which means now not every unit's being tested and or verified. So having a scope of work and having a conversation with a third party to get a scope of work could ensure that all T's are crossed, all I's are dotted, making sure everything gets verified. So having a SOW in the builder's packet telling the builder or the developer what is and isn't expected to be verified by the third party is a great way to do it. So in other words, the city would say, look, we're going to look at insulation, we're going to look at the air barrier, but that's the extent of what we're going to look at. You're going to verify blower door, duct blaster, and then also making sure that it matches the manual J, manual S, and making sure those are verified as being correct, and that the sizing matches energy modeling assumptions as well. So that's a great way to do it. So have a short list of what your building officials and inspectors are inspecting and what they are not inspecting. If that all that makes sense. And of course, on this it says, where does the liability fall? I know there's some things with the city that they possibly, a lot of it is they can't really be held liable for some things because it's basically on the shoulders of the builder to do the right thing, meeting code. They need to go study the code and make sure they're meeting code within the area that they're in, and that's why they do it. But who's responsible for it? There's a lot of them I hear a lot of times from third party is we do blower door and duct blaster only. The city doesn't do it. They do the energy stuff. We're only contracted to do blower door and duct blaster. Well, A, that's not a lot of revenue from the builder. But B, if the building's now failing a blower door at the final, who's responsible for it going wrong? If it's a complete failure of the envelope due to the air barrier not following manufacturer's instructions, and they're not using the nailing pattern on the T-ply, they're not using the tape on the seams, and it was just looked at from an insulation standpoint and moved on, and now blower door is extremely high and there's no way to get there. Just getting an approval from the city to say that's okay and that we'll do better on the next one, that home's going to have a lot of issues with size of equipment is now incorrect, and then uncontrolled infiltrations happening inside and out. And that happens more than I would like to think that it doesn't, is the fact that cities say we're going to do the energy code inspections, and I come from third party. I'm not trying to say cities should not be a part of that, but knowing who's doing what and who's responsible for what, and at one point or another is how is it going to be addressed when it's a failure at the end, is a good conversation to have with your third parties and builders in your city. And then, of course, this is what I talked about earlier. In a perfect world, this is how we would see this happen. This is kind of a checklist for the HVAC designer. This is kind of what happens. A building's going for permit. They've put all the stuff together. They've grabbed a packet. They've put things together. So before the design, they're actually confirming the project airtightness target. So in other words, what climate zone am I in? What city am I in? What's the requirement? Do I need to hit 4 ACH? Do I need to hit 5? Do I need to hit 3? So you just say, well, what's my target? Well, let's just say it's going to be 4. And so you're in a North Central Texas COG area in North Central Texas. You're using the COG amendments for the 2021, and you're getting 4 ACH. So basically you request what's the preliminary blower door results. In other words, you talk to the builder or the third party that has done work for them before and say, what is normally the air tightness of that building? Do they build a tight house, or do they have a lot of holes in those buildings? So then you coordinate with the energy rater and the modeler, and you confirm what's expected infiltration on the manual J. So then you do a manual J, you input the tested or targeted ACH, and then you adjust infiltration rate to match real world results. So you use zone specific data, not generic. You ensure accurate insulation, window value, SHGC are used and matches what the builder is actually installing. Then you make sure that the right sized HVAC equipment is based on that load calculation. Right now, you're still assuming it's a 4 ACH house. You don't know yet. You just assume that it is. So you're basing all of this on that assumption. You build all of this. You do manual J, you do manual S. You make sure the BTU output of that equipment matches BTU of the load of the manual J, and then you turn that in for permit. And then they get a permit and they start to build. And of course, at the same time, you're looking at, well, now that I know the ACH and the building tightness of this, I'm going to use the manual S and the ASHRAE 62.2 to designate and determine mechanical ventilation needs based on my blower door assumptions. And then, of course, you design the system meeting the ASHRAE 62.2 requirements. You coordinate with controls of the equipment and the specs now to adjust proper runtime. This is them just assuming and setting it up as they're installing it. And then, of course, after the design, and then when you go for a final and the third party's in there and they're testing the mechanical ventilation, which is now required for Energy Star and 2021 moving forward. Now, once you do that, you share that load calculation and the HVAC design with the installer and the rater. You include the ventilation system setup in the HVAC contractor's scope of work. You verify blower door test now meets that assumption or is at least close. It could be lower than that. So if you're trying to hit 4 and you're at 3.8, it's a little bit lower. So basically now you need to adjust that mechanical ventilation and make sure that meets the needs for that house itself. So I've yet to witness blower door results go back to the HVAC designer to ensure correct assumptions. Most of the national builders that we did a lot of work for, if they're going to try to build a house to 4 ACH, they're going to do everything that they can to be 4 or better. But sometimes it comes down to a point of we're not going to overkill it because if we now hit 2.8, we spent too much money to seal all the homes. If we're just looking for 4, we could have done less. So if they slack off just a little bit or they get a new contractor and they're not doing the same thing as they did before, well, now instead of it being 4, we're at 4.8 and you're trying to get it tighter. If it's left that way because there's no way to fix it because it's an envelope issue that's behind the cladding, brick, sheetrock, and it can't be fixed, or it's an encapsulated home with foam and you can't find the air leakage because it's the way the framing is done, you can't get to it anymore. Now the sizing is incorrect and it needs to be addressed. Changing the speed of the equipment, maybe from a high speed to a medium speed, to slow down airflow to offset the oversizing of the equipment. So I hope all of that wasn't too confusing. I tried to keep on track and not get lost in the weeds with a lot of things. I hope a lot of that made sense. What I really was trying to do was just to connect the dots as to this is why blower doors are important. But the same thing is there's another dot at the end, which means verifying that blower door met the assumptions of the manual J and S for sizing of the equipment. And if that's done, then you can rest assured, most likely, that within 10%, 15% max, you've probably got the correct size for that equipment. They don't make a system that's sized in increments small enough to meet it dead on. But let's say your sizing came in at 3.8 requirement and you sized it for a 3.5. That's not going to be detrimental. That's probably for the best because you'll have longer run times and smaller equipment means less construction costs. But if you're trying to say that your assumption is 3.8 for the sizing and your now blower door is closer to 5 and you were trying to hit 4 to get that sizing to that 3.8 and now it's off and now you're looking at closer to a 4. And if someone just says, just put a 4 on there and oversize it, now we've got an oversized equipment, means short cycling of the equipment and higher humidity than normal. So I appreciate everybody being here. Join us on our next webinar. We're going to go back, and we did this about a year and a half ago. We're going to go back and revisit water furnace and talk about some of the new technology they've got for geothermal systems to help understand the mechanics of what they do in their systems. We'll have a few more of our members as well which are LG and Daikin. That's going to also do some webinars for us to get us caught up on this heat pump stuff and geothermal and the technology that they have out there. This one's on April 29th at 10:30. Stay tuned for that. And again, as always, thanks to everyone that's been reaching out to me with questions and training requests. I really do appreciate it. If you ever have any questions or know someone with any questions, by all means, share my information with them, and I can help them with the energy code questions that they have. Don't hesitate to reach out at any time. Send me pictures from the field, and I'll be happy to use that in one of our webinars as well. So last one I'll have here is just connect with us. We are on LinkedIn, we are on X, and we are now on Blue Sky as well. So connect with us there. We got a lot of stuff that we post and go through. And I appreciate everyone being on here. Thanks for your time today. And thanks for joining our webinars. I appreciate it.